Tonight, we are going somewhere older than the continents, deeper than light, and far more alien than the desolate, cratered plains of the moon. This place resides on our world right now, yet its history remains shadowed in profound silence, almost completely erased from modern memory. We return to the forgotten, long-vanished primordial oceans of ancient Earth. It is a slow, quiet journey into the planet's lost memory, a memory preserved only through salty hints locked within deep stone and ancient, twisted basalt. Across the vast span of geological time, our world has worn many masks. We will encounter the ancient boiling seas born of poison skies, the quiet microbial waters of the prolonged Middle Eon, the pitch-black abyss sealed beneath a world of global ice, and the vast inland seaways that split landmasses we now call home. We trace the endless veil of steam that condensed to form the first oceans, the deep hydrothermal chimneys that sheltered fragile, emerging biology, the ancient rust that settled into red layers on the seafloor, and the vanished coastlines buried beneath billions of years of drifting crust. What remains of the very first waters that gave birth to terrestrial life? How do we listen to an ocean that ceased to exist billions of years ago? If this kind of slow, quiet exploration is something you enjoy, I would be grateful if you would leave a like and subscribe to Midnight Sleep Documentary. And if you would tell me in the comments where you are listening from tonight and what time it is where you are. That is always a quiet comfort to read. Now settle in, dim the lights, let your breathing slow. We are leaving the modern map behind. We tend to imagine the global ocean as a permanent fixture of our world. We picture the Pacific, the Atlantic, or the Indian Ocean stretching vast, calm, and eternal across 70% of our planet's surface, as if those exact basins have existed since the beginning of time. But the ocean basins themselves are far from permanent. They are living, breathing, geological structures that are born, broaden, shrink, and eventually are swallowed whole by the relentless engine of planetary subduction. Ocean crust is young compared to the continents. It is constantly created at mid-ocean ridges and continually consumed in deep abyssal trenches. Tonight, we become hydropaleontologists, charting waters that no longer exist, examining their hidden chemistry, their deep stillness, and the strange biology that stirred within them. To understand the story of water on Earth, we must travel back to the absolute dawn of cosmic time, over 4 billion years ago, during the violent Hadean and early Archean eons. The name Hadean reflects the inferno of Hades, and no name could be more fitting. The newborn Earth was not a calm globe of blue and green, but a chaotic world recovering from violent cosmic collisions. A thin, fragile, unstable crust floated precariously over a global ocean of boiling, molten rock. Volcanoes erupted everywhere, spouting vast, dark plumes of toxic gases into a sky choked with carbon dioxide, dense water vapor, methane, ammonia, and sulfurous fumes. No breathable oxygen existed in this atmosphere. Step onto the early Earth without protection would mean instant asphyxiation. The sun, much younger and 30% dimmer than it is today, burned weakly through a thick, yellow-orange toxic smog, unable to provide clear light. There was no ozone layer to block the unfiltered, harsh, ultraviolet radiation streaming from space. Meanwhile, large asteroids and lingering protoplanetary comets slammed into the surface continuously, blasting huge craters into the cooling mantle, vaporizing rock, and instantly boiling away any liquid water that attempted to gather on the glowing crust. Yet, within this planetary inferno, the seeds of the world's ocean were quietly gathering. Water arrived early in Earth's history, carried inside the icy interiors of incoming comets and carbonaceous asteroids, as well as released directly from the planet's deep interior through volcanic outgassing. In the intense, scorching heat of the early surface, this moisture could not settle on the ground. Instead, it existed entirely as an immense, heavy blanket of atmospheric steam, The planet was wrapped in a towering greenhouse atmosphere, so thick that the atmospheric pressure at the surface was dozens of times greater than it is today. For tens of millions of years, the Earth remained a steamed, glowing orb. But as the heavy bombardment of asteroids gradually slowed and the planet's surface cooled below the boiling point of water under high pressure, a monumental planetary shift occurred. The atmosphere reached its condensation threshold, unleashing a deluge of cosmic proportions. Rain began to fall, not as a gentle shower, but as a relentless, torrential downpour that cascaded across bare basalt, cooled the dark volcanic rock, and filled giant impact craters. This rain fell continuously for centuries, perhaps even thousands of years, filling every depression on the planet until the Earth's very first global ocean was born. We might naturally expect these initial seas to resemble the cool, clear blue waters of today's modern oceans, but that assumption quickly unravels under geological scrutiny. These primal waters were hot, acidic, and saturated with heavy dissolved metals. Born from acidic condensed steam washing over scorching, freshly solidified volcanic rock, they simmered beneath a suffocating sky. Vast quantities of dissolved carbon dioxide and sulfur dioxide made the water chemically corrosive, aggressively leaching iron, manganese, and silica from the basaltic seabed. Because there was no free oxygen present in the atmosphere or the water to react with the iron, the dissolved ferrous iron remained suspended in the water column. This gave the global ocean an eerie, pale greenish olive hue, totally unlike the cobalt blue we recognize today. The sky above was a heavy, twilight copper orange, reflecting off a vast, greenish sea that stretched from horizon to horizon, with almost no land masses to break its surface. It was not a nurturing, gentle paradise, but a dense, breathless, corrosive chemical brew. Yet inside this scorching, acidic ocean, deep beneath the surface in absolute darkness, a microscopic miracle was waiting to happen. The surface of this primordial ocean offered no safety for delicate organic molecules. The sun's ultraviolet rays battered the surface water without mercy, and occasional asteroid impacts continued to flash-boil the upper layers of the ocean. To find the sanctuary where biology first took hold, we must descend far beneath the waves, down to the abyssal ocean floor. Here, the thin volcanic crust was continually cracking open above the planet's molten interior, creating extraordinary geothermal oases, deep-sea hydrothermal vents. At these deep sites, cold, acidic seawater seeped deep into subterranean fissures within the ocean floor, penetrating kilometers into the hot basalt. As the water approached the magma chambers below, it heated to incredible temperatures, reaching hundreds of degrees Celsius without boiling due to the immense hydrostatic pressure of the deep sea above. Under these intense conditions, the water reacted violently with the surrounding rock, becoming hypercharged with dissolved minerals and gases. It became saturated with methane, ammonia, hydrogen sulfide, iron, nickel, and silica. Driven by thermal buoyancy, this superheated, mineral-dense fluid spewed back out into the freezing, pitch-black ocean depths. As the scalding fluid met the cold, alkaline seawater of the abyss, dissolved minerals instantly precipitated out of solution, constructing towering chimney structures on the ocean floor. Some of these were dark, fiery vents known as black smokers, spouting thick clouds of iron sulfide minerals into the water. Others were warmer, alkaline chimneys, similar to the modern Lost City hydrothermal field, built from porous carbonate minerals and releasing fluids rich in molecular hydrogen and methane. In this crushing darkness, miles beneath the reach of the sun, life required no sunlight to exist. Microscopic entities and primordial cellular structures gathered around the porous walls of these mineral chimneys, drawing chemical energy directly from dissolved gases like hydrogen sulfide and hydrogen. They learned to survive without photosynthesis, utilizing chemosynthesis to convert inorganic molecules into cellular energy. They constructed thin, slimy microbial mats around the vents, establishing a completely self-contained food web in absolute blackness. The porous mineral walls of the vents provided microscopic microchambers, tiny, sheltered caverns that acted as natural inorganic cells. These mineral pockets concentrated simple organic molecules, catalyzing early chemical reactions and shielding fragile emerging RNA and lipid membranes from the harsh ultraviolet radiation and impact shocks occurring at the surface. The deep ocean floor was not an empty wasteland. It was the planetary laboratory where non-living chemistry transformed into living biology. The warmth and rich chemistry of these abyssal vents offered the ultimate sanctuary for the earliest stirrings of life. But the energy driving these deep organisms followed rules completely alien to our sunlit world. To understand how these ancient microbial ecosystems endured across millions of years, we must carefully examine the fundamental chemistry of chemosynthesis, a biological metabolic process that operates entirely independent of solar light and surface conditions. On the sunlit surface of modern Earth, nearly all biological systems rely on sunlight driving the engine of oxygenic photosynthesis. Surface plants, phytoplankton, and marine algae capture incoming solar photons to transform atmospheric carbon dioxide and liquid water into complex, energy-rich carbon sugars, releasing molecular oxygen back into the atmosphere as a metabolic byproduct. But beneath the dark Archean waters, in the absolute crushing shadows of the abyssal ocean floor, life invented a radically different way to sustain its biological processes. In the extreme environment of deep-sea hydrothermal vents, early microorganisms utilized the stark, unyielding chemical gradients established between the hot interior of the Earth and the cold, dense ocean water above. The hydrothermal fluid spouting from alkaline vents contained abundant dissolved hydrogen gas and methane, while the surrounding acidic ocean held extraordinarily high concentrations of dissolved carbon dioxide. Primitive cellular organisms acted as biological conduits, channeling this stark geochemical imbalance to power their metabolic machinery. By combining molecular hydrogen directly with carbon dioxide, these primitive cells synthesized methane and complex organic carbon compounds through ancient, foundational metabolic pathways such as acetogenesis and methanogenesis. Other early microorganisms exploited the vast quantities of hydrogen sulfide, BOH2S, flowing directly out of dark, sulfurous volcanic chimneys. They systematically stripped chemical energy from the molecular bonds of inorganic sulfur compounds, using that harvested energy to fix inorganic dissolved carbon into vital cellular biomass. Rather than relying on energy emitted from a star millions of miles away, these deep-sea organisms drew their vital life energy directly from the residual heat and chemical decay of the cooling core of the Earth. The deep primordial ocean was not a passive container for early biology. It was an active, dynamic chemical engine where planetary geology continuously provided the fundamental fuel for biological metabolism. Because these early organisms evolved long before the advent of oxygenic photosynthesis, they did not produce or require free oxygen for their survival. In fact, to these ancient cellular architectures, free oxygen was a deadly, destructive toxin that would instantly oxidize and tear apart their fragile lipid membranes and primordial enzymes. The Archean ocean floor thrived with intricate, highly structured, microscopic communities organized into dense, multi-layered biofilms that coated the mineral walls of every vent chimney and volcanic fissure. Generation after generation lived out their entire existence, reproduced, and died in total, unyielding darkness, nourished solely by the geothermal heat and chemical-rich fluids issuing from the subterranean crust. Yet despite the incredible longevity of these early chemosynthetic ecosystems, which dominated the surface of our planet for hundreds of millions of years, The physical record of the Hadean and early Archean oceans has almost entirely vanished from the face of the modern world. The primary geological reason these ancient waters were forgotten lies in the violent, unending cycle of global plate tectonics. The oceanic crust of Earth is not a permanent, unyielding monument. It is a temporary, constantly recycling conveyor belt. New basaltic crust continually erupts at spreading ocean ridges, cools as it comes into contact with seawater, slowly drifts across the surface of the planet over tens of millions of years, and eventually plunges back down into the scorching mantle at deep subduction zones. Because oceanic crust is denser and heavier than continental crust, it is systematically swallowed, compressed, and remelted over continuous tectonic cycles lasting roughly 200 million years. Consequently, virtually no ocean floor older than 200 million years exists anywhere on the surface of the globe today. The physical seafloors of the Hadean and Archean eons, which existed 3 to 4 billion years ago, have been entirely destroyed, melted down, and reabsorbed into the deep, churning mantle of the planet. Furthermore, the Earth's early continental land masses were tiny, thin, and continuously broken apart by intense tectonic forces and energetic mantle plumes rising from the core mantle boundary. The ancient rocky shorelines that once felt the steady lap of those acidic, pale green waters were repeatedly crushed, cooked by thermal metamorphism, and ground down by relentless subaerial erosion. Only a few scattered, heavily distorted fragments of ancient crust, known to geologists as cratons, have managed to survive this billion-year geological meat grinder. Formations like the Isua Greenstone Belt in Greenland, the Barberton Greenstone Belt in South Africa, and the Pilbara Craton of Western Australia offer tiny, battered, and highly altered windows into this incredibly distant past. Within these rare, intensely metamorphosed rock formations, geologists must operate as forensic detectives working across immense vastnesses of time. They search for subtle, indirect chemical signatures, such as shifted isotopic ratios of carbon, sulfur, and iron locked within ancient zircon crystals, or preserved pillow basalts, rounded, tube-like rock formations that only take shape when molten lava erupts directly into cold underwater environments. Beyond these tiny, heavily altered clues, the vast expanses of the Hadean and early Archean seas have been thoroughly erased, living on only in the permanent chemical legacy they left behind within the planet's continental crust and mineral reserves. Despite their complete physical erasure from the modern surface, the legacy of these first oceans continues to shape our modern world in profound, structural ways. The most monumental and far-reaching physical contribution of those ancient, iron-rich seas was the creation of banded iron formations, commonly referred to as BIFs. For hundreds of millions of years, the green Archean oceans were saturated with vast quantities of dissolved ferrous iron, which had been continuously washed out of submarine volcanic vents and weathered from basaltic land masses. As early photosynthetic organisms, specifically primitive cyanobacteria, began to emerge and proliferate in the shallow, sunlit surface waters, they began producing free molecular oxygen as a metabolic waste product. In a modern, oxygenated ocean, this produced gas would accumulate directly in the surface water column and rapidly vent out into the surrounding atmosphere. But in the primordial Archean seas, the vast ocean was filled with dissolved iron, which acted as a colossal chemical buffer and sponge. The free oxygen produced by shallow cyanobacteria immediately reacted with the dissolved ferrous iron suspended in the water, instantly oxidizing it into insoluble ferric iron oxide. This newly created rust could no longer remain dissolved in seawater. It precipitated out of the water column in vast chemical clouds, slowly raining down onto the ancient seafloor as fine, reddish-brown iron mud. Over millions of years, as biological activity fluctuated in response to seasonal variations, shifts in oceanic currents, and changes in available sunlight, layers of oxidized iron rust alternated with distinct layers of silica-rich chert. This continuous, rhythmic process created striking, sharply striped rock deposits composed of dark red hematite or magnetic black magnetite interleaved with gray, fine-grained chert. These massive banded iron formations built up in monumental layers hundreds of meters thick across the vast, shallow seafloors of the late Archean and early Proterozoic eons. Eventually, after nearly 1 billion years of relentless chemical precipitation, the seemingly endless supply of dissolved iron in the global ocean was entirely exhausted. The green, iron-heavy seas were systematically cleansed of their dissolved heavy metal content, transforming over vast spans of time into clear, blue-green waters. Only after the oceanic iron sink was completely saturated and exhausted could free molecular oxygen escape the ocean's surface in immense quantities and begin accumulating directly within the atmosphere. A planetary transformation known as the Great Oxidation Event, which permanently altered the chemistry of Earth's atmosphere, oceans, and biosphere. Today, nearly all the iron ore mined by human civilization, from the structural steel beams forming our skyscrapers to the massive steel hulls of ocean-going ships and the long railway networks spanning continents, is extracted directly from these ancient banded iron formations deposited billions of years ago. The modern industrial world is literally built upon the oxidized, settled remains of Earth's first forgotten oceans. As the dissolved iron was swept from the ocean column and free oxygen began its slow, chaotic accumulation across the planet, the delicate chemical equilibrium of the entire globe was thrown into deep instability, setting the stage for a dramatic and unprecedented transition in planetary history. With the arrival of the Proterozoic eon, spanning from roughly 2.5 billion years ago to 540 million years ago, the Earth entered a vast, extended stretch of planetary time that geologists historically referred to as the Boring Billion. This prolonged interval, covering approximately 1.8 to 0.8 billion years before the present day, earned its deceptive reputation primarily because the planet's continental plates appeared to settle into a remarkably stable configuration. Atmospheric oxygen levels remained relatively flat, and large multicellular fossils had yet to make their dramatic appearance in the rock record. But to look at this colossal stretch of temporal history as empty, dead air is to completely miss one of the most remarkable, subtle chapters in global ocean history. Beneath a calm, deceptively uniform surface, the vast Proterozoic seas were undergoing profound, slow-burning chemical transformations that quietly laid the essential cellular and geochemical foundations for the eventual explosion of complex animal life. The world during this long Middle Age was defined by drifting land masses that gradually migrated across the globe, eventually colliding to assemble the giant supercontinent of Rodinia. As these ancient continental cratons smashed together near the equator around 1.1 billion years ago, they locked almost all of the planet's continental crust into a single, colossal landmass surrounded by empty horizon. Encompassing this single giant continent was an equally immense, planet-spanning ocean, Mirovia, a name derived from the Russian word for global or world. Mirovia was a panthalassic ocean, completely unlike any marine environment that exists on our modern globe. Because virtually all the world's continental crust was welded together into one supercontinent on one side of the planet, Mirovia stretched unbroken across an entire hemisphere, uninterrupted by major land barriers, island arcs, or broad epicontinental seas. Its deep surface currents flowed in vast, uninterrupted planetary loops, creating massive ocean gyres that spanned thousands upon thousands of miles, without ever encountering a continental coastline. With no scattered land masses to deflect warm equatorial water toward the frozen polar regions, heat distribution across this vast, endless ocean was radically different from our modern world. The interior of the supercontinent Rodinia was a vast, lifeless, rainless desert, entirely isolated from maritime moisture, while the sprawling coastal margins of Mirovia experienced long, monotonous millennia of chemical weathering, under a pale sun. In the broad, sunlit, shallow margins of Mirovia, life was far from absent. It was actively constructing extraordinary, living architecture across thousands of miles of ancient coastlines. These were the true cities of the Proterozoic eon, vast, sprawling underwater reefs made not of hard corals, sponges, or calcium-shelled animals, but constructed entirely by microscopic microbial communities known as stromatolites. Stromatolites are layered, mound-like sedimentary structures formed by the intricate metabolic activities of dense communities of microscopic, photosynthesizing cyanobacteria. In the quiet, warm, sunlit shallows of the Proterozoic coastlines, vast, velvety carpets of green microbial mats trapped fine grains of floating carbonate sediment carried in by the gentle tides. As sunlight streamed through the shallow water column, the cyanobacteria photosynthesized, changing the local water chemistry and precipitating calcium carbonate directly out of the seawater, which effectively cemented the trapped sediment grains into hard, rock-like microbial structures. Day after day, generation after generation, the microscopic organisms migrated slowly upward toward the sunlight to avoid being buried, leaving behind thin, concentric, fossilized layers of laminated limestone beneath them. Over thousands of years, these microbial mounds grew into vast, submerged forests of stone. Some formed smooth, rounded domes, while others developed into tall, finger-like columns, heavy biological knobs, or complex, branching, tree-like structures rising several feet from the muddy seafloor. For thousands of miles along the sunlit continental shelves of Mirovia, these stromatolite reefs stretched unbroken, serving as the dominant biological features on the entire planet. They were the primary biological engine of the Proterozoic Earth, churning out a continuous, slow stream of molecular oxygen into the shallow surface waters, while steadily absorbing atmospheric carbon dioxide into their mineralized limestone structures. If one could stand on those distant, rocky shores and wade into these ancient, shallow seas, it would reveal a marine ecosystem of immense, silent order and profound stillness. There were no fish darting between the stone columns, no crabs crawling across the limestone surfaces, no seaweeds swaying in the tidal currents, and no sounds save for the steady rhythm of water hitting stone. There was only the endless repetition of green, slimy, living stone domes resting in crystal-clear waters, illuminated by a pale sun beneath a light copper-tinted sky. These microbial architects worked in total biological isolation, building massive structural reefs across the globe for over 1 billion years without ever encountering a single grazing herbivore or burrowing organism to disturb their growth. However, this long era of apparent planetary stability was not destined to endure forever. Deep beneath the calm surface of Mirovia, the chemical stratification of the water column was becoming increasingly tense and toxic, preparing to spark a catastrophic crisis in the ocean's global biological engine. The structure of Mirovia's deeper waters was fundamentally broken into distinct, non-mixing layers, a condition known as chemical ocean stratification. While the very top layer of the sunlit ocean contained low levels of oxygen generated by the shallow stromatolite reefs, the vast, deep ocean abyss remained completely devoid of oxygen. Even more critically, intermediate ocean depths became heavily enriched in dissolved hydrogen sulfide, creating a toxic, anoxic, and sulfidic condition that geologists refer to as a Canfield Ocean, named after the geochemist Donald Canfield, who first proposed this planetary state. In this sulfide-rich ocean environment, key trace metals like molybdenum, copper, and zinc were chemically stripped from solution, precipitating out into the deep seafloor sediments as insoluble metal sulfides. Because these specific trace metals are essential micronutrients that complex life forms and advanced nitrogen-fixing bacteria require to construct enzymes, their extreme scarcity in seawater created a severe biological bottleneck. The open ocean was effectively a biological desert, severely limiting the evolution of eukaryotic cells, cells with complex nuclei and organelles, and keeping the planet trapped in a long evolutionary waiting room. For nearly 1 billion years, complex cellular life could not expand beyond tiny, isolated niches. The ocean was locked in a delicate, stagnant chemical balance, shallow microbial reefs clinging to the continental edges, surrounded by a vast sulfidic ocean that choked off advanced evolution. But deep geological forces were slowly grinding away beneath the crust, preparing to shatter the supercontinent of Rodinia and rip this stable oceanic system apart. As thermal energy built up beneath the massive insulator of Rodinia's thick continental plate, giant mantle plumes began to push upward against the underside of the landmass. The supercontinent started to stretch, crack, and tear open along immense rift valleys. Seawater rushed into these expanding continental rifts, creating narrow new seas that would eventually widen into vast ocean basins. This intense tectonic breakup exposed millions of square miles of fresh volcanic rock to rain and atmospheric weathering, initiating a catastrophic sequence of global chemical feedback loops. The intense chemical weathering of these newly exposed basalts drew vast amounts of carbon dioxide out of the atmosphere, locking it away in ocean sediments as carbonate minerals. As the atmospheric greenhouse gas blanket was stripped away, global temperatures plummeted rapidly, sending shockwaves through the stagnant waters of Mirovia. The long, quiet age of the stromatolite reefs was drawing to a sudden and violent close as the ocean prepared to freeze solid from the poles to the equator. To fully grasp how the vast Proterozoic seas operated across this prolonged interval, we must look much closer at the deep, hidden chemical crisis that held the ocean in its tight grip. The Great Oxidation Event had introduced free molecular oxygen to the atmosphere and the shallowest surface waters, but it did not instantly transform the entire ocean into a uniform, clear, and breathable environment. Instead, it created a stark, highly unstable, three-tiered chemical system across the global water column. At the very surface, a thin skin of sunlit water held modest amounts of dissolved oxygen generated by shallow stromatolite reefs. Directly below that sunlit layer, extending across vast intermediate ocean depths, resided the Canfield Ocean, a warm, stagnant, oxygen-starved zone heavily saturated with toxic, foul hydrogen sulfide produced by vast populations of anaerobic, sulfate-reducing bacteria. Down in the deepest abyssal trenches and ocean floors, conditions remained completely anoxic, lingering in absolute darkness without a single trace of free oxygen. This severe, multi-layered chemical stratification had disastrous, far-reaching consequences for early biological evolution. The vast quantities of hydrogen sulfide continuously rising from the intermediate ocean layer reacted constantly with essential dissolved heavy metals suspended in the water, such as molybdenum, zinc, copper, and iron. These chemical reactions forced those precious trace elements to precipitate out of solution, settling onto the dark seafloor as insoluble metal sulfide minerals. Modern biological enzymes, the microscopic molecular machines that enable living organisms to fix nitrogen, process genetic material, build protective cell walls, and manufacture essential metabolic proteins, depend heavily on these specific trace metals to function properly. With those essential micronutrients permanently locked away within thick marine sediments, early life suffered from a chronic, planetary-scale nutritional deficit that lasted for hundreds of millions of years. The vital process of biological nitrogen fixation was particularly crippled by this metal shortage. The specialized soil and aquatic bacteria, responsible for converting inert atmospheric nitrogen gas into bioavailable nitrate and ammonia, rely almost entirely on complex, molybdenum-bearing enzymes. Because dissolved molybdenum was extraordinarily scarce within the sulfide-heavy Proterozoic oceans, primary biological productivity ground to a near-total halt across the open sea. The expansive, deep-water regions of the global ocean Morovia were vast, crystal-clear biological deserts, where microscopic life could barely manage to scratch out a fragile existence. The biological engine of the Earth was running on empty, trapped in a severe chemical bottleneck created largely by the toxic metabolic waste products of its own early microbial inhabitants. Because of this prolonged interval of apparent evolutionary and environmental stasis, 20th century geologists historically dubbed this entire period the Boring Billion. They pointed directly to the flat, unchanging carbon isotope curves recorded in sedimentary carbonate rocks, the apparent lack of major evolutionary leaps or multicellular animal fossils, and the long, quiet pause in global mountain-building events as clear evidence of a dormant, stagnant planet. But modern, high-precision geochemical analysis and isotopic mapping have revealed that this era was far from a dead, empty waste. Beneath its calm, uniform exterior, it was a period of intense, slow-burning biological refinement and crucial cellular innovation. While the ocean surface appeared calm and unchanging across endless millennia, microscopic life was quietly undergoing a profound, revolutionary internal transformation. The severe ecological pressure imposed by planetary nutrient scarcity forced primitive single-celled organisms to adapt and innovate in ways that would forever change the trajectory of life on Earth. Up until this point in biological history, life had consisted almost exclusively of simple prokaryotes, uncomplex, single-celled organisms like bacteria and archaea that lacked internal membrane-bound compartments or organized genetic nuclei. But within the quiet, stress-filled waters of the sunlit Proterozoic shallows, a momentous biological event took place: endosymbiosis. In a quiet, microscopic struggle for survival, one predatory single-celled host organism engulfed a smaller, free-living aerobic bacterium. Instead of digesting the smaller cell as a routine food source, the host organism established a mutually beneficial, permanent symbiotic relationship with its captive tenant. Over vast spans of time, that engulfed bacterium evolved into the mitochondrion, the specialized cellular powerhouse capable of generating massive amounts of biochemical energy using oxygen. Later in the eon, another lineage of these complex host cells engulfed a photosynthesizing cyanobacterium, which eventually evolved into the chloroplast, enabling plant and algal ancestors to harness sunlight directly. This single, extraordinary evolutionary leap birthed the very first eukaryotic cells, much larger, infinitely more complex cellular structures equipped with dedicated nuclei, intricate internal membrane networks, and the immense cellular energy capacity required to construct complex multicellular bodies. Far from being an empty evolutionary dead zone, the quiet, nutrient-starved Proterozoic ocean was the crucial planetary incubator where complex cellular machinery was meticulously designed, tested, and perfected. Without the intense environmental pressures, nutrient constraints, and chemical stresses imposed by the Canfield Ocean, complex eukaryotic life might never have evolved on our world at all. Beyond the fundamental creation of the eukaryotic cell, another revolutionary biological tool emerged within the quiet Proterozoic waters: true sexual reproduction. Primitive prokaryotic organisms reproduced almost entirely through simple binary fission, cloning themselves endlessly with minimal genetic variation from one generation to the next. But as eukaryotic organisms diversified within the quiet microenvironments of the stromatolite reefs, they developed meiosis and sexual recombination. This new, highly sophisticated reproductive strategy allowed individual organisms to continuously mix genetic material from two distinct parents, creating completely unique genetic combinations in every single generation. Instead of waiting millions of years for rare, random genetic mutations to introduce beneficial new traits, life could now rapidly recombine existing traits, exponentially accelerating the overall rate of evolutionary adaptation and biological diversity. This groundbreaking development provided early microscopic organisms with the immense genetic flexibility required to survive unpredictable shifts in global ocean chemistry, water temperatures, and localized nutrient availability. Additionally, simple multicellular structures began making their very first tentative appearances within the fossil record during the latter half of this quiet era. Exceptional red algae fossils, such as Bangiomorpha pubescens, remarkably preserved in ancient rock formations of Arctic Canada, demonstrate that as early as 1 billion years ago, individual cells were learning how to adhere firmly together, specialize their biological functions, and form organized multicellular filaments. Microscopic testate amoebae also began constructing delicate protective shells from tiny mineral grains trapped in their environment, marking humanity's very first glimpse into the origin of biomineralization and hard body protection. These quiet, momentous evolutionary breakthroughs were taking place beneath a deceptive, serene surface of planetary calm. Microscopic life was steadily assembling the entire genetic and cellular toolkit needed to eventually build complex, visible animals. The essential genes governing cell adhesion, intercellular communication, specialized tissue development, and systemic energy transport were all forged inside the nutrient-deprived, sulfide-laden waters of the Proterozoic eon. While the boring billion provided the slow, steady incubator required for these complex cellular tools to mature, the planet's underlying geological engine was silently preparing a sudden, radical disruption. Deep beneath the ocean floor, the giant supercontinent of Rodinia was beginning to tear itself apart along massive continental rift zones, exposing millions of square miles of fresh basaltic rock to the elements, and setting off an unprecedented geochemical chain reaction across the entire globe. As atmospheric carbon dioxide levels began to fall rapidly due to the relentless chemical weathering of these newly exposed volcanic rocks, the warm, quiet Proterozoic seas were about to experience a planetary freeze so severe and profound that it would nearly extinguish life on Earth entirely. As the massive supercontinent of Rodinia began to break apart into smaller, isolated landmasses roughly 720 million years ago, it triggered the onset of the Cryogenian period, a time defined by the most extreme and dangerous climate disasters in the entire history of our planet. As vast continental rifting opened up thousands of miles of fresh tropical coastlines, torrential rains fell continuously across freshly exposed continental basaltic lava flows. This massive exposure of reactive rock initiated a colossal, planetary-scale chemical weathering reaction. Atmospheric carbon dioxide dissolved into rainwater to form carbonic acid, which reacted aggressively with silicate minerals in the rock, drawing down immense quantities of greenhouse gases directly out of the atmosphere and trapping them permanently as carbonate sediments on the shallow seafloor. Stripped of its insulating atmospheric blanket, the Earth began to cool rapidly and uncontrollably. Great polar ice sheets expanded outward from the high latitudes, moving steadily and relentlessly down toward the equator. This rapid expansion of sea ice set off a dangerous, runaway climate loop known to scientists as the ice albedo positive feedback mechanism. Pure white snow and sea ice possess an extremely high albedo, reflecting roughly 80 to 90% of incoming solar radiation directly back into space, whereas dark, open ocean water absorbs nearly all of the sun's thermal energy. As floating sea ice crept farther away from the poles and reached into the mid-latitudes, it reflected an ever-increasing fraction of solar energy away from the surface, which in turn accelerated global cooling at an exponential rate. Once the encroaching ice sheets crossed a critical mathematical threshold, roughly 30 degrees north and south latitude, the runaway feedback loop became entirely unstoppable. Massive glaciers surged across the remaining warm tropical waters, finally meeting at the equator and completely sealing the entire planet inside a thick, crushing shell of surface ice hundreds of meters to over a kilometer thick. The Earth had transformed into a complete, brilliant, white snowball Earth. For tens of millions of years during the two back-to-back global ice ages known as the Sturtian and Amarinoan glaciations, the global ocean Mirovia lay entombed beneath a dark, impenetrable, and crushing roof of solid ice. The familiar, comforting rhythms of the open sea ceased to exist entirely. There were no crashing ocean waves breaking on sandy shores, no wind-driven surface currents sweeping across the basins, no coastal tides washing through sunlit estuaries, and no direct exchange of gases between the surrounding atmosphere and the massive body of water below. Beneath this continuous frozen ceiling, the entire abyssal ocean was plunged into a state of total, uninterrupted blackness. Sunlight could not penetrate through hundreds of meters of dense, crystal-hard glacier ice, bringing photosynthetic primary production to a sudden, absolute halt across the entire globe. The delicate, oxygenated surface skin of the sea quickly vanished, leaving the vast, deep ocean below to stagnate. Free atmospheric oxygen could no longer dissolve into the water column, while underlying geothermal vents continuously spewed reduced gases, toxic sulfur, and heavy dissolved metals directly into the abyss. Deprived of any oxygen input from above, the vast, silent body of the Mirovia Ocean reverted to a dark, completely anoxic, and iron-heavy primordial state. Yet, despite the crushing atmospheric pressure and the complete absence of sunlight, the oceans did not freeze solid all the way down to the seafloor. The deep interior heat of the Earth, continuously generated by radioactive isotope decay within the planet's core and mantle, continued to radiate steadily upward through the thin oceanic crust. This constant geothermal energy, combined with the immense insulating properties of the overhead ice sheet, kept a massive, global liquid ocean alive and moving beneath the ice. It was a strange, silent, subterranean world. The deep ocean currents were no longer driven by global wind patterns or atmospheric solar heating, but by powerful thermal convection currents rising from deep volcanic spreading ridges and active geothermal vent fields on the seabed. Plumes of scalding, mineral-dense water rose from the ocean floor, circulating slowly beneath the dark ice ceiling before cooling, shifting horizontally, and descending back into the abyssal depths. The global ocean had effectively turned inward, drawing its circulation, physical movement, and thermal balance entirely from the planet's internal geothermal heat engine rather than from the light of the sun. For early eukaryotic life, microscopic algae, and soft-bodied single-celled organisms, this prolonged frozen era was an ultimate biological test of survival. With the surface waters frozen solid and the vast majority of the open ocean devoid of both light and dissolved oxygen, life was pushed to the absolute brink of total planetary extinction. Yet, against impossible odds, life did not perish. It adapted by seeking out extreme micro-refuges scattered sporadically across the frozen globe. One critical refuge existed around deep-sea hydrothermal vents on the abyssal seafloor. Just as during the Hadean and Archean eons billions of years prior, the abyssal vent fields served as warm, chemical-rich oases amid a hostile, freezing planetary environment. Chemosynthetic bacteria thrived around these black and white smokers, feeding on hydrogen sulfide and methane while providing a stable, reliable food source for early single-celled eukaryotes that gathered around the mineral chimneys in total, crushing darkness. Another vital sanctuary existed far above the ocean floor, in narrow, slushy polynyas and supraglacial melt ponds. Near active volcanic island arcs and exposed coastal zones, geothermal heat, volcanic ash deposits, and localized seasonal melting created temporary open water gaps in the ice sheet. Sunlight managed to penetrate these thin, slushy patches, allowing small, resilient populations of photosynthetic algae and cyanobacteria to survive and maintain basic metabolic activity. Additionally, Cryoconite holes, tiny melt pockets formed on the surface of glaciers filled with wind-blown dark dust and organic material, provided microscopic aquatic habitats where tiny ecosystems clung to life, suspended precariously between the frozen sky and the dark sea below. These isolated marine refuges acted as high-pressure genetic pressure cookers for biological adaptation, completely cut off from one another by thousands of miles of impassable, solid ice. Isolated populations of eukaryotic cells underwent rapid genetic drift, intense selection pressures, and localized evolutionary experiments. The intense environmental stress eliminated weak, inflexible biological lineages, while heavily favoring organisms equipped with advanced cellular structures, tough outer membranes, complex genetic repair mechanisms, and flexible metabolic pathways. Furthermore, as massive continental glaciers slowly ground across the underlying land masses, they crushed millions of cubic miles of solid rock into extraordinarily fine, mineral-rich dust. This glacial flour, saturated with highly bioavailable iron, phosphorus, nitrogen, and essential trace elements, accumulated in vast quantities along the underside and edges of the ice sheets, waiting for the inevitable day when the frozen roof would finally break apart. The global ocean remained locked inside this icy prison for tens of millions of years, its deep water chemistry slowly and dramatically changing as subterranean geothermal vents continuously pumped iron, manganese, and phosphorus into the oxygen-starved depths, setting the stage for a dramatic, catastrophic global thaw. As geothermal carbon dioxide slowly built up in the atmosphere from unhindered volcanic eruptions, unable to be absorbed by the frozen oceans, the greenhouse effect eventually reached a breaking point. The massive accumulation of atmospheric carbon dioxide would soon trigger a super greenhouse effect, heating the planet to scorching temperatures and causing the thick global ice sheets to melt with terrifying speed. When the global thaw finally arrived, the sudden release of millions of years of locked-up glacial flour and bioavailable nutrients into the newly exposed oceans produced a massive, unprecedented biological nutrient bloom. The dark, isolated, and stagnant waters of the Cryogenian were suddenly inundated with abundant sunlight, warm surface temperatures, and an unimaginable feast of dissolved minerals. This sudden, catastrophic shift in ocean chemistry and energy input shattered the long biological stasis that had held the planet in check. The resilient eukaryotic cells that had spent tens of millions of years trapped within dark, isolated refuges were suddenly released into a global, nutrient-rich marine playground, setting off a rapid evolutionary radiation that would forever transform the structure of life on Earth. The legacy of these frozen oceans was not death, but a fundamental biological reboot. The extreme evolutionary bottleneck of the Cryogenian period cleared away simple ancestral microbial structures and forged the resilient, highly adaptable cellular machinery that would soon build the very first complex, multicellular animals of the Ediacaran and Cambrian eras. While the planet lay encased in its thick, reflective shell of solid surface ice, the vast global ocean trapped beneath was far from inactive. Completely locked away from the Earth's atmosphere for millions of years, the dark, pressurized waters of the global Morovia Ocean transformed into a giant, subterranean chemical reactor operating in absolute darkness. Deep-sea volcanoes, mid-ocean spreading ridges, and active hydrothermal vents along the abyssal seabed continued to erupt and discharge uninterrupted, spewing massive quantities of carbon dioxide, methane, foul hydrogen sulfide, and dissolved ferrous metals directly into the stagnant, unaerated water column. Because there was no free molecular oxygen present in the deep ocean to react with these reduced chemical compounds, and no open surface boundary to vent volatile gases into the sky above, the overall concentration of dissolved metal ions and reduced compounds reached extraordinary, unprecedented levels. Over millions of years, the deep ocean became hypersaturated with bioavailable iron, manganese, sulfur, and soluble phosphorus, a potent, highly pressurized chemical soup continuously building up beneath hundreds of meters of solid glacial ice. At the very same time, high above the dark, frozen roof of the ocean, planetary geology was quietly assembling the physical mechanism required for its own liberation. Volcanic structures piercing through the continental ice sheets continued to pump vast quantities of carbon dioxide, sulfur dioxide, and other heat-trapping gases directly into the thin, frozen atmosphere. In a normal, ice-free planetary regime, this volcanic carbon dioxide would be steadily absorbed by falling rainfall and drawn down into the oceans through the chemical weathering of surface silicate rocks. But on a completely frozen snowball Earth, with the global ocean sealed beneath ice and continental rainfall virtually halted across the frozen land masses, there was no effective chemical sink available to strip carbon dioxide out of the air. Century after century, million after million years, volcanic carbon dioxide accumulated unchecked within the atmosphere, eventually reaching terrifying concentrations hundreds of times higher than those observed in modern times. Eventually, the relentless atmospheric greenhouse effect grew so intense and powerful that it began to overwhelm the high reflective albedo of the global snow and ice cover. The thermal tipping point arrived with sudden, catastrophic intensity across the globe. Tropical equatorial zones began to warm, and dark, dusty meltwater pools formed across the surface of the equatorial ice sheets, absorbing vast amounts of solar radiation and accelerating the melting process exponentially. Within a few thousand years, a mere blink of an eye in geological time, the thick global ice sheet completely disintegrated. The glaciers melted with unimaginable, catastrophic speed, dumping billions of tons of fresh meltwater, crushed rock dust, and long-trapped debris directly into the ocean basins below. The dark, subglacial ocean was exposed to direct, radiant sunlight for the first time in tens of millions of years. The sudden, violent aftermath of this global ice collapse triggered an unprecedented planetary event, the post-glacial nutrient bloom. As the vast, multi-kilometer-thick continental glaciers rapidly retreated across the landmasses, they released an unimaginable volume of accumulated glacial flour, extraordinarily fine, pulverized rock dust, rich in iron, phosphorus, potassium, calcium, and trace elements that had been ground down beneath the moving ice sheets over tens of millions of years. Torrential, acid-tinged rains, driven by an extraordinarily hot, hyper-warm greenhouse atmosphere, washed this nutrient-dense glacial dust directly off the bare continents and carried it straight into the newly exposed coastal waters. The powerful combination of abundant, direct sunlight, warm surface ocean temperatures, and an extraordinary, sudden spike in dissolved ocean phosphorus and iron created the greatest biological feeding frenzy in the entire history of Earth. Microscopic photosynthetic algae and single-celled cyanobacteria experienced an explosive, unprecedented population explosion across the globe. Giant phytoplankton blooms covered millions of square miles of the ocean surface, turning the warm coastal waters thick, murky, and vibrant green. Through intense, unchecked oxygenic photosynthesis, these massive algal blooms absorbed immense volumes of atmospheric carbon dioxide and released unprecedented, soaring waves of molecular oxygen directly into both the shallow surface waters and the surrounding air. This massive, rapid influx of biological oxygen reacted violently with the mineral-heavy ocean water that had slowly built up during the long, dark subglacial freeze. Dissolved ferrous iron and manganese ions were instantly oxidized upon contact with the oxygenated surface waters, precipitating out of solution in vast chemical clouds and raining down onto the shallow seafloor to create extensive, late Proterozoic cap carbonates and thick, iron-rich sedimentary rock beds. As excess atmospheric carbon dioxide was rapidly scrubbed from the air by intense rock weathering and biological activity, locking it safely away into vast, thick limestone beds, the planet's volatile climate eventually stabilized into a warm, oxygen-rich equilibrium. The cryogenian glaciations, though brutal, terrifying, and nearly fatal to early life, fundamentally reset the structural, biological, and chemical architecture of planet Earth. The extreme, unyielding evolutionary bottleneck imposed by the millions of years freeze had eliminated simple, inflexible microbial competitors, while the nutrient-rich, hyper-oxygenated post-glacial aftermath provided the exact geochemical fuel and energy reserves required for massive biological expansion. For the very first time in 4 billion years of planetary history, the deep ocean layers contained high enough concentrations of dissolved molecular oxygen to support larger, complex, multicellular cellular structures. Living organisms were no longer strictly limited to microscopic, single-celled sizes or thin, flat microbial mats clinging to rocks. The abundant, easily accessible dissolved phosphorus allowed living cells to construct complex lipid cell membranes, synthesize dense chains of DNA and RNA, and manufacture vast quantities of adenosine triphosphate, or ATP, for rapid internal cellular energy transfer at speeds and efficiencies never before possible in Earth's history. The ocean was permanently transformed from a stagnant, stratified, and toxic chemical brew into a dynamic, highly oxygenated, and nutrient-dense environment, fully prepared to foster the evolution of multicellular animals. In the quiet, warm, post-glacial, shallow waters of the Ediacaran period that directly followed the thaw, the very first true multicellular animals made their gentle, quiet debut in the fossil record. Strange, soft-bodied organisms, quilted living fronds anchored to the seabed, flat, circular discs resting on the sediment, and segmented, quilted mats, known collectively to science as the Ediacaran biota, began to spread across the shallow, sunlit, muddy seafloors worldwide. They possessed no hard protective shells, no eyes, no specialized digestive tracts, and no limbs, absorbing dissolved organic nutrients directly through their soft cellular tissues as they rested peacefully upon the calm ocean floor. These gentle, slow-moving Ediacaran organisms lived in a quiet ocean ecosystem that lacked aggressive predators, burrowing hunters, or complex food webs. They grazed peacefully on thick, velvety microbial mats that still covered large portions of the seafloor, forming a bizarre, tranquil biological world that paleontologists often refer to as the Garden of Ediacara. For tens of millions of years, these soft-bodied fronds and mats represented the absolute pinnacle of animal complexity on Earth, flourishing in shallow, clear seas that were warm, rich in oxygen, and free from the threat of large-scale predation. However, beneath this serene, peaceful surface, the competitive landscape of the ocean was slowly beginning to change once again. Life was developing new genetic toolkits, complex nervous systems, and specialized cellular structures that would soon allow organisms to move faster, manipulate their environment, and actively hunt other living creatures for energy. The gentle, soft-bodied world of the Ediacaran biota was living on borrowed time as the ocean prepared for an evolutionary explosion that would forever destroy the quiet peace of the primeval seas. The dark, frozen nightmare of the cryogenian oceans had passed into history, leaving behind a clear, brilliant blue, oxygen-rich sea that had finally set the geochemical and biological stage for the great, violent animal revolutions of the upcoming Cambrian period. As these soft-bodied Ediacaran communities thrived in the quiet, shallow waters, the planet's underlying tectonic plates were already shifting once again, driving broad continental flooding, creating vast new shallow water shelf environments, and generating the intense ecological pressures that would soon give birth to modern, hard-shelled marine ecosystems. Following the dramatic global thaw of Snowball Earth, the vast oceans of the Ediacaran period, spanning roughly 635 to 539 million years ago, entered an unprecedented era of open biological experimentation. Across the warm, sunlit continental shelf environments, the very first multicellular complex organisms flourished in a serene, peaceful marine world that scientists often refer to as the Garden of Ediacara. These ancient creatures were soft-bodied, delicate, and entirely unlike any modern animal group living in our oceans today. Elegant, frond-like organisms, such as Charnia, anchored their basal stalks firmly into the fine, muddy seafloor, swaying gently in the slow, rhythmic coastal currents, while circular, disc-shaped organisms like Cyclamedina rested quietly upon thick, velvety microbial mats. Oval, quilted creatures like Dickinsonia crept along at a glacial pace across the biological carpet, absorbing organic matter directly through their soft underside tissues without the assistance of a mouth, stomach, or internal digestive tract. This ancient, primeval marine ecosystem operated under a completely different set of ecological rules than the oceans of today. There were no active predators pursuing fleeing prey, no sharp teeth or crushing jaws designed to tear tissue, no eyes scanning the murky depths for danger, and no hard, mineralized structures anywhere within the entire water column. Animals lived in peaceful, passive coexistence with the underlying microbial mats, dense, gelatinous sheets of bacteria and microscopic algae that sealed the ocean floor like a continuous, rubbery carpet. Because these early multicellular animals lacked complex internal organ systems, dedicated respiratory organs, or specialized circulatory networks, they relied entirely on basic diffusion, absorbing dissolved nutrients and dissolved oxygen directly through their high surface area tissues. For tens of millions of years, this soft-bodied, gentle fauna represented the absolute pinnacle of animal complexity on Earth, thriving in shallow, highly oxygenated waters under conditions of absolute ecological tranquility. As we look closer at these bizarre, tranquil marine communities, we find an ecosystem completely devoid of modern dynamic interactions. The seafloor was not yet disturbed by digging claws, churning feet, or predatory jaws. Instead, these organisms existed in a static, two-dimensional landscape, absorbing energy directly from the organic films beneath them or filtering organic dust gently out of the passing currents. The waters above were pristine, clear, and quiet, undisturbed by fast-swimming creatures or active hunters. It was a brief, fragile moment in the history of our planet where life expanded in complexity without the immediate evolutionary pressure to defend itself, escape from harm, or capture other living beings for survival. Yet, this gentle, soft-bodied world was quietly harboring the biological seeds of its own total destruction. Towards the final few millions of years of the Ediacaran period, a subtle yet profound chemical and biological shift began to unfold within the shallow continental seas. Living organisms began experimenting with a revolutionary new biological technology, biomineralization. For the first time in 4 billion years of planetary history, multicellular animals learned how to actively extract dissolved calcium and carbonate ions directly from seawater and precipitate them into solid, hard, mineralized body structures. Small, cone-shaped organisms like Claudina and trumpet-like organisms like Nemacalathus began constructing delicate, interlocking tube-like shells made of solid calcium carbonate to protect their soft internal tissues from environmental stress and mechanical disruption. The emergence of hard, mineralized shells marked the definitive, irreversible end of the peaceful Ediacaran regime and signaled the dramatic birth of evolutionary arms races. While early mineral shells may have initially evolved to provide simple structural support or protection against fluctuating water chemistry, they quickly transitioned into functional defensive armor. For the very first time in the geological fossil record, microscopic fossils display tiny, neat, circular boreholes drilled directly through the mineralized outer walls of Cloudina. Shells, unmistakable physical evidence of predatory organisms actively attacking, penetrating, and consuming hard body armor to eat the soft animal inside. The arrival of biomineralization shattered the peaceful stasis of the primeval seas, initiating a high-stakes evolutionary warfare between hunter and hunted that would accelerate the rate of biological diversification at a staggering, unprecedented speed. This new mineralized architecture completely redefined what it meant to survive in the primeval ocean. Where soft tissue once drifted unprotected in the current, solid shells now provided shelter, leverage for movement, and protective barriers against aggressive chemical environments and hungry neighbors. Organisms were no longer purely passive participants in their ecosystems. They were becoming active builders, constructing hard mineral fortresses around themselves, and developing the physical tools necessary to break through the fortresses of others. This fundamental breakthrough in biological construction laid the structural foundation for virtually every protective shell, sharp claw, supportive skeleton, and defensive spine that would dominate the ocean waters for the next 500 million years. As hard armor was making its initial appearance within the water column, an equally profound, catastrophic shift was taking place directly within the seafloor sediment beneath. For billions of years, the ocean bed had been sealed tight by unbroken, rubbery microbial mats, creating an abrupt, impenetrable chemical boundary between the oxygenated water column above and the dark, toxic, oxygen-deprived sediment below. But near the close of the Ediacaran period, primitive worm-like organisms developed functional muscular systems, complex fluid-filled hydrostatic skeletons, and bilateral symmetry, allowing them to perform a simple yet radical action. They began to burrow horizontally and vertically directly into the soft mud. This biological invasion of the seafloor sediment sparked what paleontologists and geologists call the Great Agronomic Revolution, or the Agronomic Substrate Revolution. Organisms like Treptichnus pedum began actively churning, mixing, and tunneling through the top layers of the seafloor, breaking through the ancient, sealed microbial mats and mixing oxygen-rich surface water directly into the dark, sulfurous mud below. This process of intense biological bioturbation completely destroyed the ancient mat-covered ocean floor, forever altering the physical and chemical nature of the marine substrate worldwide. Sediments that had been compact, sticky, smooth, and completely anaerobic for billions of years were systematically loosened, aerated, and ventilated by millions of burrowing creatures seeking organic food particles and protection from surface predators. The destruction of the universal microbial mats had catastrophic, apocalyptic consequences for the soft-bodied Ediacaran biota. The delicate fronds, anchored discs, and quilted mats that depended entirely on a stable, unbroken, rubbery surface to rest upon found their structural anchors destroyed, their feeding surfaces buried in loose silt, and their specialized habitats disrupted by the constant, relentless churning of the mud. As the old soft-bodied fauna vanished into rapid extinction, the newly churned, oxygenated sediment opened up vast new three-dimensional ecological habitats for burrowing, crawling, and surface-dwelling animals. The ocean floor was no longer a flat, two-dimensional stage. It had permanently transformed into a complex, multi-layered ecosystem where animals could swim through the water, walk across the seabed, or bury themselves deep within the aerated seafloor mud. As these burrowing organisms turned the seabed into a dynamic, three-dimensional realm, the entire chemical cycling of the global ocean was fundamentally rewired. Nutrients that had remained trapped beneath dark, oxygen-starved mud for billions of years were suddenly churned back up into the water column, feeding vast new communities of surface organisms. The deep sediments, now supplied with a constant stream of dissolved oxygen brought down by active burrowers, became viable living space for complex life rather than toxic, lifeless waste zones. Life had not merely adapted to the physical conditions of the ocean floor, it had actively dismantled the old geological layout and built a vastly more complex, interconnected, and dynamic ecosystem in its place. This fundamental transformation of the seafloor substrate, combined with the rise of active predation and hard-shell architecture, completely dismantled the ancient Proterozoic marine order. The stage was now fully set for an explosive, unprecedented surge in complex biological diversity, specialized body plans, and aggressive animal behaviors. As the quiet, soft-bodied world of the Ediacaran faded away into the rock record, vast global sea levels began to rise dramatically, flooding the low-lying continental platforms with warm, nutrient-dense shallow seas, setting up the most famous, violent, evolutionary explosion in the entire history of planet Earth. Driven by rising global sea levels and tectonic shifts, vast continental margins were submerged under shallow, clear tropical waters, creating sprawling marine epicontinental seas that were saturated with calcium, oxygen, and rich mineral nutrients. In these expansive, sunlit, shallow environments, life was no longer constrained by simple structural forms or passive feeding strategies, opening the door for complex sensory organs, advanced limbs, and hard exoskeletons. The ancient, tranquil seas had officially come to an end, yielding to an intense, highly dynamic arena where speed, vision, strength, and armor would dictate which species survived and which faded into fossilized history. The stage was set for a dramatic evolutionary leap that would see the sudden appearance of virtually every major animal phylum known to science today, transforming the ocean from a quiet nursery into a dynamic, competitive arena. With the arrival of the Cambrian period, roughly 539 million years ago, the global oceans experienced the most violent, rapid, and revolutionary biological event in the entire history of planet Earth. Over a span of merely 20 to 30 million years, a brief, fleeting moment in geological time, virtually every major animal body plan, or phylum, known to modern science emerged simultaneously within the warm, sunlit, shallow seas. Driven by soaring atmospheric oxygen levels, abundant dissolved calcium and phosphorus, and the total collapse of the old Ediacaran ecosystem, life exploded outward in a bewildering, radical array of complex anatomical forms. Soft-bodied, stationary filter feeders were rapidly replaced by fast-moving arthropods, swimming mollusks, complex echinoderms, and early chordates possessing primitive backbones. This unprecedented evolutionary outburst was fueled by the sudden, intense acceleration of the world's first true evolutionary arms race. For the first time, animals developed sophisticated compound eyes, long sensory antennae, jointed limbs for rapid locomotion, and sharp, chitinous jaws designed specifically for biting, crushing, and severing tissue. In response, prey organisms developed increasingly thick external skeletons, defensive spines, heavy mineralized plates, and complex burrowing behaviors to escape detection. The ocean was no longer a quiet, stagnant sanctuary where living organisms absorbed nutrients passively from passing currents or underlying microbial mats. It had permanently transformed into a dynamic, highly lethal three-dimensional battlefield where visual acuity, movement speed, physical strength, and impenetrable body armor dictated the exact terms of individual survival. As we examine this profound transformation, we see how every layer of the ocean was suddenly filled with intense, competitive interactions. Organisms were no longer living in isolation or operating under peaceful, passive rules. The water column above was crisscrossed by swift swimming hunters, while the seabed below was populated by armored crawlers, equipped with sharp spines and thick carapaces. The chemical nutrients dissolved in seawater were being actively converted into dense mineral shells, intricate jointed limbs, and complex nervous systems capable of processing real-time visual information. This dramatic surge in biological complexity completely reorganized the flow of energy through the marine environment, creating multi-tiered food webs that linked microscopic plankton at the surface directly to massive, predatory carnivores patrolling the open water. The physical ocean floor itself became an intricate landscape of offense and defense. Where creatures once lay flat on soft mats, they were now forced to continuously negotiate a hazardous terrain populated by specialized hunters. Some species evolved elaborate camouflage patterns along their dorsal carapaces to blend seamlessly into the sandy seafloor, while others developed long, sensitive antennae capable of detecting minute pressure changes in the surrounding water. Every bodily structure, from the curve of a leg segment to the thickness of a shell wall, was refined through relentless natural selection. The quiet, calm environment of the primeval seas was gone forever, replaced by an ecosystem where vigilance was the absolute prerequisite for existence. At the absolute apex of this dangerous new marine world swam Anomalocaris, the world's first giant targeted super predator, measuring up to 1 meter in length, an enormous, terrifying size compared to the tiny, inch-long creatures crawling across the mud beneath it. Anomalocaris dominated the Cambrian water column with absolute authority. Equipped with a pair of large, highly sensitive compound eyes mounted on flexible stalks, it possessed a level of visual perception never before seen in planetary history. Beneath its head, 2 large, spiny, flexible appendages were used to grab swimming or crawling prey and pull it directly into a strange, circular, disc-like mouth lined with overlapping plates of sharp, serrated, chitinous teeth. Using long, overlapping lateral fins that rippled smoothly along the sides of its streamlined body, Anomalocaris glided effortlessly through the open water column, actively hunting trilobites, primitive arthropods, and soft-bodied worms. The presence of Anomalocaris completely reshaped the behavioral landscape of the ocean, forcing every other living creature to adapt or perish. Its relentless hunting pressure drove the rapid evolution of complex evasive maneuvers, protective schooling behaviors, heavy external exoskeletons, and buried lifestyle strategies among its prey. The calm, two-dimensional marine world was permanently gone, replaced by a complex ecological hierarchy topped by a fast, visually guided open-water killer. The rise of such a massive, specialized hunter demonstrated that the ocean had acquired the ecological capacity to support complex, top-tier predators for the very first time. Anomalocaris was not merely an opportunistic scavenger drifting along with the current. It was an active, highly mobile hunter, capable of tracking movement across long distances, maneuvering precisely through the water column, and physically overpowering heavily armored prey. Fossilized trilobite shells from this era frequently exhibit severe, healed bite marks that perfectly match the circular, crushing jaw structure of Anomalocaris, providing direct, physical evidence of failed predatory attacks and ongoing evolutionary battles between hunter and prey. This formidable top predator operated as an evolutionary catalyst across all levels of the marine food network. By selectively hunting slow or poorly defended individuals, Anomalocaris applied continuous pressure on prey populations to improve their defense systems. In response, trilobites developed thicker calcified exoskeletons, compound eyes capable of looking upward into the open water, and the ability to roll into tight, armored balls when threatened. Other smaller arthropods responded by developing spiny protrusions along their sides, making them difficult or painful for Anomalocaris to swallow. Thus, the top predator did not merely consume life, it actively sculpted the anatomical trajectory of the entire marine ecosystem. The extraordinary diversity and structural complexity of this revolution are preserved with astonishing, delicate clarity in the fossil beds of the Burgess Shale in North America and China's Zhenjiang deposits. Because these ancient coastal marine communities were periodically swept away by sudden underwater mudslides and buried instantly in fine, oxygen-deprived silt, even the most delicate soft tissues, including primitive guts, delicate gills, internal organs, individual eye lenses, and slender swimming fronds, were preserved down to microscopic levels of detail. Within these soft sediment fossil beds, paleontologists have uncovered a bizarre, alien world populated by animals that defy simple classification. Creatures like Opabinia drifted above the seabed, hunting with 5 stalked eyes and a long, flexible trunk tipped with a grasping claw. The terrifying, needle-spined Hallucigenia walked across the muddy ocean floor on stilt-like legs, while arrays of sharp defensive spines guarded its back from attack. Alongside these bizarre evolutionary experiments swam tiny, translucent, eel-like creatures called Picaia. Lacking hard shells, large claws, or crushing jaws, Picaia possessed a simple, flexible rod running along its back, a primitive notochord, marking it as one of the earliest known ancestral chordates, the foundational, evolutionary branch that would eventually give rise to fish, amphibians, reptiles, birds, and mammals. The exceptional preservation found within these ancient shale formations provides an unprecedented window into an ecosystem in the midst of rapid, chaotic creation. We see a multitude of experimental body plans, many of which represented unique evolutionary branches that vanished entirely without leaving modern descendants. Other forms, however, established the fundamental anatomical templates that would define animal life for the next 500 million years. The presence of soft tissue structures, like delicate digestive tracts, complex gills, and intricate nervous systems, proves that internal biological systems were expanding in complexity just as rapidly as external armor and sensory organs. As we linger over these ancient fossil impressions, we begin to appreciate the sheer breadth of biological innovation occurring in these sunlit, mud-floored seas. Each layer of fine shale acts as a snapshot, frozen in time, capturing tiny, soft-bodied worms, swimming arthropods, and delicate sponges in their original living positions. The delicate outlines of gills and internal fluid vessels show that respiratory and vascular systems were evolving rapidly to sustain higher metabolic rates and active lifestyles. The Burgess Shale does not merely show us what these animals looked like, it shows us an entire, fully functional community caught in mid-motion during life's most dramatic morphological leap. The ecosystems of the Cambrian period established the fundamental structural blueprint for modern marine life. Ocean waters were now thoroughly stratified into specialized, highly competitive ecological zones, with active predators patrolling the sunlit surface waters, swift swimmers darting through the middle depths, bottom dwellers crawling across the sediment, and deep burrowers tunneling safely within the muddy substrate. The ancient primeval ocean had completed its long, multi-billion-year transformation, evolving from a sterile, chemically simple fluid into a complex, vibrant, and interconnected biological realm, brimming with energy, competition, and infinite structural possibilities. This intricate stratification allowed thousands of distinct species to coexist within the same geographical regions by occupying highly specific ecological niches. Some organisms specialized in filtering tiny floating particles from the upper water column, while others grazed on microalgae carpeting the seafloor or dug deep trenches into the sediment to extract organic detritus. This remarkable division of labor within the marine environment vastly increased the overall efficiency of the global biosphere ensuring that energy and carbon were cycled rapidly through complex biological pathways rather than remaining stagnant in dead ocean sediments. With energy cycling through these complex ecological pathways, the ocean reached a new state of dynamic balance. The presence of deep burrowers continuously churned oxygen into the sediment, preventing the return of stagnant, sulfur-choked ocean beds. Meanwhile, the constant activity of surface swimmers and bottom grazers ensured that biological nutrients were continuously recycled throughout the water column. The ancient, primitive ocean had truly matured into a modern biological system, capable of supporting immense populations, driving rapid evolutionary changes, and recovering from localized environmental disruptions. Yet, even as these early marine communities reached unprecedented heights of anatomical complexity and ecological diversity, the planet's relentless tectonic plates were quietly preparing the next major geological shift, rearranging the continents and setting up sweeping climatic changes that would soon test the resilience of this vibrant, armor-clad marine world. Driven by vast tectonic forces, the ancient landmasses were slowly drifting together toward the South Pole, altering global ocean currents, triggering dramatic cooling trends, and threatening to alter the warm, shallow seas that had nourished this spectacular biological revolution. The tranquil, warm, tropical seas of the Cambrian were approaching an inevitable climatic boundary, where shifting ocean currents, falling sea levels, and descending polar temperatures would soon challenge every creature that had fought so hard to survive in this new, predatory world. As cold water began to creep northward from the polar regions, the vast epicontinental seas that had nurtured the Cambrian explosion began to shrink, forcing marine life into increasingly narrow coastal corridors and triggering the first major post-Cambrian environmental crisis. The stage was slowly being set for a global cooling event that would test whether these newly evolved body plans possessed the resilience to endure widespread environmental collapse. Following the initial, explosive biological surge of the Cambrian period, the global ocean entered the Ordovician period, spanning roughly 485 to 443 million years ago. During this remarkable era, the planet experienced an even more sustained, expansive, and profound diversification of marine life known to science as the Great Ordovician Biodiversification Event, or GOBE. While the preceding Cambrian period had successfully established the fundamental anatomical body plans of animal life, the Ordovician period filled those basic body plans with unprecedented evolutionary richness, quadrupling the total number of marine animal genera and multiplying the overall ecological complexity of the global seas by orders of magnitude. Soaring sea levels flooded the low-lying continents to record geological depths, creating sprawling, warm, sunlit epicontinental seas that stretched across vast equatorial regions, providing the ideal marine conditions for a magnificent flourish of complex life. This massive biological diversification was driven by fundamental shifts in global ocean circulation, long-term climate stability, and widespread nutrient availability across the planet. The drifting continents, including the giant southern supercontinent of Gondwana, were positioned in ways that generated powerful, continuous upwelling ocean currents. These deep, nutrient-dense currents brought vast reserves of dissolved phosphorus, nitrate, iron, and silica from the abyssal seafloor straight up into the sunlit surface waters. Planktonic communities flourished on a monumental scale, providing a rich, reliable, and endless biological food source that supported complex, multi-tiered marine food webs. The ocean was no longer just a collection of shallow, isolated coastal margins. It had evolved into a fully integrated, deep-water biological system where life inhabited every single level of the water column, from the floating planktonic clouds of the open ocean to dense benthic communities thriving on the deep seafloor. Within these rich, sunlit, and nutrient-dense Ordovician seas, A formidable new group of intelligent, highly mobile predators rose to absolute dominance, the giant orthoconic cephalopods, direct biological ancestors of modern squids, octopuses, cuttlefish, and nautiluses. Remarkable creatures like Camaraceras constructed long, straight, cone-like shells made of heavy calcium carbonate, with some massive specimens reaching lengths of over 6 meters. Unlike the slower, bottom-dwelling predators of the Cambrian period, these giant cephalopods were active, powerful, open-water swimmers. They possessed highly sophisticated internal buoyancy controls, using a specialized, living vascular tube called a siphuncle to precisely adjust the gas and fluid levels within the individual chambered sections of their heavy shells, allowing them to glide effortlessly through any depth of the ocean without expending excessive physical energy. Equipped with large, highly developed eyes capable of processing sharp images in low-light environments, flexible muscular tentacles, and powerful, parrot-like chitinous beaks, Camaraceras and its close relatives quickly replaced Anomalocaris as the undisputed apex predators of the global ocean. They patrolled the open water column with calm authority, actively preying on primitive jawless fish, heavy trilobites, and large marine arthropods. Their emergence applied continuous, intense evolutionary pressure across the entire marine ecosystem, driving prey species to develop faster swimming abilities, thicker defensive armor, more effective camouflage mechanisms, and complex schooling behaviors. The open ocean had permanently transformed into a dynamic, highly competitive realm governed by speed, depth control, visual acuity, and tactical intelligence. At the very same time, the physical structure of the ocean floor was undergoing a parallel architectural revolution through the rise of the world's first true coral strome reef systems. Unlike the simple microbial mounds of the Proterozoic Eon or the fragile, isolated sponge reefs of the Cambrian period, Ordovician reefs were massive, highly complex biological fortresses constructed by a cooperative assembly of bryozoans, rugose corals, tabulate corals, and massive, wave-resistant stromatoporoid sponges. These calcifying organisms extracted enormous quantities of dissolved calcium and carbonate ions directly from seawater, cementing their mineralized skeletons firmly together to form extensive, rugged structures that stretched for thousands of miles across warm, shallow continental shelves worldwide. These ancient coral strome reefs created an extraordinary diversity of complex microhabitats, offering shelter, breeding grounds, structural protection, and abundant food for thousands of specialized marine species. Brachiopods anchored themselves by the millions to the hard coral structures. Sea lilies, known as crinoids, formed dense, swaying underwater meadows that filtered organic particles from the passing coastal currents, and primitive, armored jawless fish, like Astraspis, darted safely through the sheltered, intricate crevices of the reef matrix. The rapid rise of these complex reef ecosystems exponentially increased the overall carrying capacity of the global oceans, providing the spatial and ecological framework required to sustain the massive species diversity generated by the Great Ordovician Biodiversification Event. For nearly 40 million years, these warm, highly oxygenated, and nutrient-dense Ordovician oceans represented an unprecedented golden age for marine life. Global biological productivity reached historic highs, and the structural complexity of marine food webs grew to rival that of modern tropical ecosystems. But deep beneath this vibrant, thriving surface, the planet's relentless geological, tectonic, and orbital engines were quietly shifting, setting the stage for a sudden, catastrophic environmental collapse that would bring this golden age to a freezing, brutal halt. The giant southern supercontinent of Gondwana was drifting slowly but steadily southward toward the Earth's south pole. As this massive landmass centered directly over the polar region, it began to accumulate vast, continent-scale ice sheets. Unlike sea ice, which floats directly on the ocean water without altering global sea level, the massive growth of thick ice caps resting on solid land locked away millions of cubic kilometers of water, causing global sea levels to plummet rapidly worldwide. The broad, shallow epicontinental seas that had nurtured and sustained Ordovician life for tens of millions of years began to drain away rapidly, leaving once vibrant coral reefs exposed to the dry, open air and utterly destroying the primary habitats of shallow water marine species across the globe. This rapid, intense glaciation triggered the late Ordovician mass extinction, officially marking the first of the catastrophic Big Five mass extinction events in the history of planet Earth. The collapse unfolded in two distinct, devastating, back-to-back waves of destruction. The first devastating wave hit as global temperatures plummeted uncontrollably, driving cold polar waters deep into the tropical equatorial regions and completely destroying the warm water ecosystems that had come to dominate the planet. Species that had adapted to stable, warm, tropical climates were wiped out in massive numbers. Simultaneously, the sudden drop in sea level drained the continental shelves, shrinking the available living space for shallow water marine communities to a tiny, crowded fraction of its former size. The second brutal wave struck several 100,000 years later as the massive polar ice sheets rapidly melted and global temperatures surged wildly upward once again. The sudden, massive influx of cold, freshwater meltwater disrupted global ocean thermohaline circulation patterns, causing deep, stagnant, toxic, and anoxic bottom waters to surge upward into the shallow coastal zones. Oxygen levels within the shallow water column collapsed almost completely, suffocating thousands of resilient species that had managed to survive the initial global cooling phase. When this multi-stage environmental crisis finally passed, more than 85% of all marine species had been completely erased from the face of the planet. The vast, thriving coral-strewn reefs were reduced to dead, eroded limestone rubble. The giant orthoconic cephalopods were severely decimated in number, and thousands of distinct trilobite, brachiopod, and bryozoan lineages vanished forever into the silent rock record. Yet, despite this overwhelming, planetary-scale devastation, the fundamental structural blueprint of marine ecosystems endured. The surviving biological lineages, including primitive jawless fish, resilient mollusks, adaptable arthropods, and deep-water survivalists, held the genetic codes needed to rebuild the global ocean once again. The dark, freezing waters of the late Ordovician Ice Age eventually receded into geological history, leaving behind a scarred, emptied, but remarkably resilient global ocean ready to begin the long, slow process of biological recovery and setting the stage for the rise of armored fish and the first tentative steps of life toward the dry land. As the global climate stabilized and warm, shallow seas flooded the continents once again during the Silurian and Devonian periods, the surviving marine life began to rapidly adapt to a transformed world where jawed fish would soon rise to claim the open water column, transforming the ocean into an arena of unprecedented physical speed, mechanical power, and predatory agility. Driven by relentless natural selection and newly evolved jaw mechanisms, these early fish would break free from the ocean floor, mastering active swimming and developing complex internal skeletons that would forever alter the balance of power in the ancient seas. The stage was set for a spectacular golden age of marine vertebrates, where massive armored sea monsters and swift, nimble hunters would push the physical limits of life in the water to heights never before witnessed in Earth's history. As the planet recovered from the bitter cold of the late Ordovician freeze, the global ocean entered the Silurian and Devonian periods, spanning roughly 443 to 359 million years ago. This era ushered in a glorious, transformative epoch in ocean history, widely known to science as the Age of Fishes. For more than 100 million years, early vertebrate life had been restricted to small, jawless, bottom-dwelling creatures like Astraspis, which spent their lives filtering organic detritus and microscopic debris out of the seafloor mud. But within the warm, sunlit, and expansive seas of the Devonian, life achieved a fundamental mechanical and evolutionary breakthrough that permanently altered the trajectory of animal evolution: the origin of the functional jaw. The functional jaw evolved through the gradual, ingenious modification of the forwardmost cartilaginous gill arches, which were the internal structural supports that previously held open the respiratory gill slits of primitive jawless fish. By hinging these sturdy bone arches and anchoring them with powerful, newly evolved muscle networks, nature successfully converted a simple respiratory breathing apparatus into a devastating physical weapon. Animals were no longer limited to sucking up loose surface organic particles or filtering tiny planktonic organisms from the surrounding water column. They could now grab, bite, hold, slice, tear, and crush large, active prey items with immense, unprecedented mechanical force. This mechanical revolution triggered an explosive biological radiation of jawed fish species known collectively as gnathostomes. Among the most formidable and imposing of these early jawed vertebrates were the placoderms, a remarkably diverse group of heavily armored fish whose entire head and forward trunk were encased in thick, jointed plates of solid bone. At the absolute apex of this Devonian marine ecosystem swam Dunkel, a massive, terrifying placoderm predator that reached total body lengths of up to 10 meters and weighed well over 4 tons. Dunkel possessed no true, isolated teeth in the modern biological sense. Instead, its massive, hinged jaws were equipped with heavy, self-sharpening blades of exposed, serrated jawbone. When Dunkel snapped its jaws shut with explosive speed, it generated a localized bite force of over 5,000 newtons at the sharp tip of its shearing blades, easily capable of slicing through the heavy mineral armor of contemporary placoderms, giant arthropods, and large cephalopods. Furthermore, its specialized internal jaw mechanics allowed it to drop its lower jaw in a tiny fraction of a second, creating a powerful internal pressure vacuum that sucked free-swimming prey straight into its gaping maw before they could react. Alongside these heavy, armored placoderms, other revolutionary fish groups were rapidly diversifying across the Devonian water column. The acanthodians, commonly known as spiny sharks, filled the middle levels of the water column, while early cartilaginous fish, the direct ancestral forebears of modern sharks, skates, and rays, began patrolling the open seas with sleek, hydrodynamic bodies and continuous rows of replaceable, razor-sharp teeth. Simultaneously, the bony fish split into 2 foundational, highly successful evolutionary lineages: the ray-finned fish, which would eventually expand to dominate modern aquatic ecosystems worldwide, and the lobe-finned fish, whose fleshy, muscular fins contained the precise, sturdy bone arrangements that would later allow vertebrates to drag themselves out of the water and take their first tentative steps onto dry land. While jawed vertebrates were mastering the art of active, high-speed predation within the open water column, a quiet, monumental revolution taking place on the dry land above was preparing to deal a catastrophic blow to the global marine ecosystem. During the Middle and Late Devonian periods, primitive land plants underwent a massive, sweeping evolutionary expansion, transforming bare, rocky continental interiors into the planet's very first dense, seed-bearing forests. While this broad greening of the continents paved the way for terrestrial animal life, its immediate biological impact on the underlying oceans was extraordinarily destructive. As deep-rooted trees, woody shrubs, and complex root systems spread aggressively across the continents, they physically broke up solid rock, creating deep, nutrient-rich terrestrial soils for the very first time in planetary history. These plants secreted powerful organic acids that dramatically accelerated the chemical weathering of continental silicate minerals. When torrential rains fell across these newly forested landmasses, immense quantities of dissolved terrestrial nutrients, particularly bioavailable phosphorus, potassium, and nitrate, were washed off the land and carried by massive river networks straight into the shallow, epicontinental seas. This sudden, massive influx of land-derived organic nutrients caused widespread, severe eutrophication across global coastal waters. Microscopic marine algae and surface cyanobacteria experienced explosive, uncontrolled population blooms that choked the surface ocean across millions of square miles. As these billions of tons of dense algal mats died and sank down into the underlying water column, vast colonies of aerobic bacteria consumed immense quantities of dissolved oxygen in order to decompose the decaying organic matter. Oxygen levels within the shallow seas collapsed almost completely, creating vast, suffocating dead zones that blanketed the continental shelves around the world. This sprawling biological crisis culminated in the late Devonian mass extinction, around 372 million years ago, an event marked primarily by the Kellwasser and Hangenberg extinction pulses. The sudden, catastrophic collapse of dissolved oxygen struck shallow water communities with terrifying force. The grand coral strome reef systems that had flourished across the globe since the Ordovician period were completely decimated, and the massive, armored placoderms, including the mighty apex predator Dunkel osteus, were wiped off the face of the Earth entirely. Deep water species and highly adaptable, small-bodied bony fish managed to survive the ordeal, but the sunlit shallow ocean was once again reduced to a silent, oxygen-starved graveyard. Following the slow, painstaking biological recovery from the late Devonian crisis, the Carboniferous and Permian periods saw the Earth's drifting continents gradually merge into one giant, continuous supercontinent named Pangaea. Surrounding this singular, colossal landmass was Panthalassa, a continuous global ocean that spanned nearly an entire hemisphere of the planet. For tens of millions of years, rich, complex marine communities flourished along the tropical, sheltered coastlines of Pangaea. But at the close of the Permian period, roughly 252 million years ago, the planet experienced the absolute climax of biological destruction, the Permian-Triassic mass extinction, an event rightfully remembered by paleontology as the Great Dying. The primary trigger for this ultimate planetary nightmare was a colossal, sustained series of volcanic eruptions occurring in what is now modern-day Siberia. Known as the Siberian Traps, these massive volcanic fissures spewed over 3 million cubic kilometers of molten basaltic lava out across the landmass over hundreds of thousands of years. Worse still, the rising subterranean magma burned directly through thick underground deposits of ancient coal, oil, and methane hydrates, releasing trillions of tons of carbon dioxide, sulfur dioxide, and toxic greenhouse gases directly into the global atmosphere. The resulting atmospheric greenhouse effect surged wildly out of control, causing global surface ocean temperatures to increase by more than 10 degrees Celsius in a geological blink of an eye. As the surface ocean water warmed to extreme levels, its physical capacity to hold dissolved life-sustaining oxygen plummeted dramatically. The global thermohaline ocean circulation engine of Panthalassa ground to a complete halt, turning the vast global ocean into a stagnant, stratified, and lifeless pool. Deprived of oxygen, anaerobic bacteria that thrived in the deep abyssal mud produced vast, deadly clouds of toxic hydrogen sulfide gas, which surged upward into the shallow surface waters, poisoning almost everything in their path. Simultaneously, the massive atmospheric absorption of carbon dioxide turned the global ocean water intensely acidic, dissolving the calcium carbonate shells of corals, brachiopods, and mollusks before the living animals could even construct them. The Great Dying unfolded with ruthless, absolute efficiency across every oceanic basin. Over 96% of all marine species were completely erased from the face of the planet within a few 100,000 years. The ancient, resilient trilobites, after surviving every previous extinction event for nearly 300 million years, were wiped out forever. Tabulate corals, giant sea scorpions, and countless ancient lineages of fish vanished entirely into the dark, sulfurous sediments of the seafloor. Yet, even in the absolute darkest hour of Earth's biological history, when the global ocean was reduced to a warm, acidic, sulfurous void, life refused to be extinguished completely. The fragile 4% of marine species that somehow managed to endure the horror of the Permian Great Dying, tiny, adaptable bivalves, resilient sea snails, primitive bony fish, burrowing sea urchins, and deep-water survivalists, clung stubbornly to existence in small, isolated environmental refuges scattered across the vast expanse of Panthalassa. As the catastrophic volcanic eruptions of the Siberian Traps finally ceased and the atmosphere cooled, the planet's geochemical cycles began the long, arduous process of stabilization once again. Over millions of years, during the subsequent Mesozoic and Cenozoic eras, those few surviving marine lineages expanded outward to slowly repopulate the emptied ocean basins. The direct descendants of those resilient Permian survivors evolved into the swimming ichthyosaurs, plesiosaurs, and ammonites of the Jurassic seas, and eventually into the magnificent whales, dolphins, sea turtles, coral reefs, and vibrant fish communities that fill our modern ocean basins today. When we stand upon the shore today and look out over the vast, shimmering expanse of the blue ocean, we are not merely looking at a simple body of salt water. We are gazing upon a living, breathing archive of planetary memory, a continuous 4 billion-year chemical, geological, and biological legacy. The iron that carries life-giving oxygen through our human bloodstream was forged inside ancient stellar cores and dissolved within the Archean seas. The precise balance of sodium, potassium, and chloride ions circulating within our own body cells is a direct, living sample of the primeval fluid where our single-celled ancestors first learned to capture energy. Every breath of oxygen we take is a timeless gift from the ancient cyanobacteria that oxidized the Proterozoic seas, and every single bone in our internal skeleton carries the precise structural blueprint forged by Devonian fish swimming through long-vanished continental shelves. The oceans of Earth have endured freezing snowball planet states, toxic sulfurous stagnations, catastrophic asteroid impacts, and world-altering volcanic warming events. Through every single environmental collapse, the global ocean has remained the eternal, beating heart of Earth, a resilient, self-renewing biological matrix where life continuously reinvents itself, quietly carrying the memory of its primeval past forward into an infinite, unfolding future.